Okay, good morning. Robotics are very advanced, and we've seen presentations yesterday, today about integrating of ICs, integrating of sensors supported by AI. But there is one bottleneck that still remains, and that's the electronics. Yeah? Electronics are still rigid, bulky, fragile. If we look at robots, for example, humanoids, or this prosthetic leg that you see here, you see rigid PCBs, you see bulky electronics, you see cables. Yeah? And if we move further to industrial applications, for example, like we have a robotic arm here on stage, but also on screen you see that there are dangling cables that can block your vision, that can cause dangerous situations, and that can maybe break. Yeah? So the question today is, can we come up with electronics that are not rigid, not fragile, but that are soft and stretchable, that can be conformed to your machine, such that it can survive real-world applications? Well, that's what we are doing with our liquid metal stretchable electronics. If you look at the device, we start with a stretchable substrate, and on that substrate we deposit our liquid metal. The liquid metal is an alloy of gallium, indium and tin. It's fluid at room temperature and it's metallic. And it integrates or interconnects the components that you put inside, like LEDs, but also to the outside readout electronics. And in the end we encapsulate everything again with a stretchable material such that everything is encapsulated. And this way we can make devices that you can stretch, you can integrate electronics. And to show you, I have this demo here where you see that we can really stretch it far. Yeah? So not only 10% or 20%, but really like a few hundreds of percent of its original length. In principle, the liquid metal stretchable electronics behaves like a natural skin. So we can say artificial skin or electronic skin. And to show that, we will show a few demos to show the properties of this electronic skin. So the first one we'll see here is this robotic arm on which we have this dangling cable. So if the robot will move and it bends, you have the option that the cable will break. The liquid metal stretchable electronics that you see here, it's stretchable, it's connected to our LEDs, and when you move the robotic arm, it conforms to the robot, it moves along, it stretches, and it doesn't break. But stretchability and conformability alone is not enough for the skin. What is also important is that it survives real-world applications. And in real-world applications, things get damaged. If you look at skin gets damaged as well, but it heals. And that's where we work with this polymeric material. It's a self-healing material based on Diels-Alder chemistry. And what happens if you cut it and you put it back together, it heals. You can use a mild thermal treatment and it heals. But much more important is that the liquid metal inside, which is fluidic, doesn't flow out. And that has to do with the fact that the liquid metal has a very high surface tension and it creates a very thin oxide skin around it. So it doesn't leak out, but when you put it back together, it flows, it's still fluidic, so it flows together, it restores its functionality. This means you have longer lifetimes of your devices and less maintenance. So our liquid metal stretchable electronics can survive real-world applications. On top of that, what skin also does is that skin will, let me say that we will check the demo here, that skin also senses. And our liquid metal material can be used as a sensing material. So what Ratul is now showing is a glove on which on each finger we have integrated a stretchable sensor. So at the moment that Ratul is moving his fingers, you'll see that the device will generate the stretching, it will sense it, and you can monitor that. And that can be used also for robotic interaction, because if Ratul now closes his hand, he makes a fist, then the robot itself will open and close like you see. The gripper above will open and close. So we translate human motion into robotic action. So that's what we do nowadays with our liquid metal. We make stretchable devices that you can use as a cable, but we also work towards integration of sensors, of ICs, of batteries, such that you can make smart patches that you can use for example, body monitoring or wound monitoring applications. Much more than that, you can also think about agri-tech. For example, we use the device as a stretchable sensor to monitor the growth of fruit from its very small stage to see when we need to do thinning of the fruit up to the harvest. Or you can think about applications on which you have a touch sensor or a pressure sensor onto your robotic gripper and you feel where the robot hits the tree. So these kind of applications we are working on already, but if you look farther in future, what is possible is that you create safe environments in industry where, let's say, movement of robots can be done in a safe environment. Or if you look at surgery, you can say that natural gestures of the surgeon will give action to the robots to do your surgery. And that's what we do today, looking at liquid metal, stretchable electronics to replace the bulky, rigid and fragile electronics that we have in robotics today, and try to bring it to soft, stretchable and self-healing devices. So we create stretchable electronics like skin for the next generation of devices. Thank you.